Greetings! This lecture is about friction and systems of mass. So we're going to use the same tricks that we used before with systems of mass. We're just going to have to add in some more forces involved acting on the system, and that force is going to be, or those forces are going to be friction. Okay, so here we've got our setup. We are pulling on one block with some force pull. Let's call this guy M1 and this guy M2. And we want to know what the acceleration of the system is. And there is friction now acting between the tabletop and M1 and M2. All right, so let's assign some numbers here. Let's say that M1 is equal to 5 kilograms. M2 is equal to 10 kilograms. Let's say that our force push is 50 newtons. And how about a coefficient of kinetic friction, because the blocks are sliding, of 0.3. And both blocks are made of the same material, so they both have the same coefficient of kinetic friction. Starting place for us is going to be to draw the free body diagram for both of the blocks. And then we're going to look at the system as a whole. So we've got M2G going down. We have the normal force acting on block 2. We have force pull on block 2 to the right. We have tension on block 2 going back to the left. And we also have the force of kinetic friction on block 2 going back to the left. M1, we've got M1G. We have the normal force acting on 1. We have the tension in the rope going to the right for M1. And we have the force of kinetic friction going back. And we should probably label these. This is the force of kinetic friction on block 2. This is the force of kinetic friction on block 1, because they're going to be different, assuming, well, we know the masses are different, the normal forces are different, the forces of kinetic friction are going to be different. All right, so remember that the trick we used for systems of mass is that we imagine the entire system, both masses, as just one mass. Okay, and we look at the external forces acting on the system. What's pulling it in the positive direction, what's pulling it in the negative direction. And we don't have to really assign a positive direction here because it's the same as our normal sign conventions. To the right is positive, to the left is negative. So forces acting on the system to the right. We have the force pull forcing the system to the right. The two tensional forces cancel out, so those we don't care about, which means that the only other forces acting, we have the two frictional forces. We've got Fk from block 1, and we have Fk from block 2, going back to the left. All right, so this actually turns out to be a relatively easy problem. We look at the sum of the forces acting in the x direction on the system are equal to the mass of the system as a whole times its acceleration. And the forces that are acting in the x direction are labeled in our free body diagram. So we have force pull minus the friction from block 1 minus the friction from block 2. That's equal to the total mass of the system, which is going to be 15, 10 plus 5 times A. Now, where the free body diagrams for the individual masses come into play is in finding Fk1 and Fk2. So going back up to our free body diagrams up here, this Fk2 is going to be the normal force on block 2 times the coefficient of kinetic friction. Fk1 is going to be the normal force on block 1 times kinetic friction. So let's throw those in down here, sorry, times the coefficient of kinetic friction. Let's throw those in down here. So F1 is going to be mu sub k times the normal force on 1. And F2 is going to be mu sub k times the normal force on block 2. Going back up to our free body diagrams, the normal force on block 2 is equal and opposite to the weight of block 2. Because there's no acceleration vertically, sum of the forces vertically is 0, so they are equal and opposite. Same thing for block 1. Normal force on 1 is m1 times g. So let's plug all that fun stuff in. We have the force of friction for block 1 is equal to mu sub k times m1g. And the force of friction for block 2 is equal to mu sub k times m2g. So now we can plug those into our Newton's second law expression over here on the right. We have force pull minus mu sub k times m1g minus mu sub k times m2g, and that's equal to 15 times A. We're solving for the acceleration of the system, so we just need to divide both sides by 15, and we've got acceleration is equal to all that stuff on the left divided by 15. So let's plug in some numbers here. Fp is 50 newtons minus the coefficient of kinetic friction, which is 0.3, times m1, which is 5, times 9.8, minus the coefficient of kinetic friction, which again is 0.3, times m2, which is 10, times 9.8. And that whole thing is divided by 15. And plugging that in the calculator, that's going to give us A. So we end up with 0.393 meters per second squared is equal to the acceleration of the system. All right? And we can also now go back up to our free body diagrams. Since we know the acceleration of each block is going to be 0.393 meters per second squared, we can solve for now the tension in the rope using either the free body diagram for M1 or the free body diagram for M2. Let's go ahead and use M1 since that free body diagram is a little bit simpler. So again, here's M1. He's got M1G going down, the normal force on block 1 going up, tension to the right, and kinetic friction back to the left. So the sum of the forces acting in the x direction on block 1 are equal to block 1's mass times his acceleration. And the sum of the forces acting in the y direction is going to equal 0 because the block's not accelerating vertically. Plugging in the forces acting in x, we have tension to the right minus kinetic friction to the left is equal to the mass of block 1 times his acceleration, which remember is 0.393. And in the y direction, normal force is going up. The weight of M1 is going down, and that's equal to 0. Plugging in what we know, well, let's not plug in anything yet. Let's solve for A over here on the left. We're going to divide both sides by M1. So tension, oh, we don't need to solve for A. Sorry, go back. Big eraser. We already solved for A. We need to solve for the tension. Sorry about that. Tension, we're going to add force of kinetic friction to both sides. M1A plus Fk. Plugging in the equation for kinetic friction, we've got M1A plus the coefficient times the normal force on block 1. Going over here on the right to the y's, N1 is equal to mg. Plugging that in down here, M1g, to be specific. For the normal force, we end up with the tension in the string is M1 times A plus the coefficient times M1G. M1 is 5 kilograms, A is 0.393, coefficient is 0.3, M1 again is 5 kilograms, and G is 9.8. So we know everything on the right-hand side. We can plug them in and solve for T. Piece of cake. All right, that's about it. We've got other situations that you're going to see, especially on the homework. You can have this kind of thing right here, where there's friction between this block, call him M1, and he's connected by a string to M2. Obviously, no friction there. And when we draw the free body diagram for this system, again, in these cases, we've got to define our positive direction. Wow, that was a weird sign. We got to define our positive direction. Let's say it's in the direction that M2 accelerates, going downward. So the forces acting on this system, we have M2G going to the right, and we're going to have the force of kinetic friction on M1 going back to the left. So that would be the free body diagram for the system here. And we could even have really tons of fun with something like this, a block on a ramp connected by a string to a block down here, and there's friction involved here as well. And you certainly should be able to deal with this. It's not necessarily fun. When we look at the system as a whole, if this is the positive direction, we've got, let's say we still have M2 and M1. We still have M1's weight moving the system in the positive direction. There is now, let's see here, a frictional force on M1, Fk1, going down the ramp, and we've got a component of M1's weight going down the ramp as well. And so over here, acting to the left, sorry, this is M2G, not M1G, it's the weight of M2. We've got the force of kinetic friction on block 1, and we also have mg, what is it, sine theta. That's the x component of m1's weight, or the component going down the ramp, that is also acting to the negative direction. Okay? So really only 3 forces to consider here. Plug them into Newton's second law. All right? So friction just adds a little extra layer of complication to these problems. You certainly can get them done. All right? Show me your notes next class, and that'll be worth 10 points. We're going to work problem sets in class next time. See you then.